Thanks very much. It's great to be here. And what we want to do today is basically take a look at some concrete solutions to the problems that we have heard about this morning. And what we're going to do is take a look at something called the cradle-to-grave analysis, or life cycle analysis, or LCA for short. And it basically is a way, a complicated bookkeeping exercise to figure out what the most favorable fuel might be if we take everything into account. In other words, in the conventional gasoline world, that would be looking at drilling the stuff, transporting it from wherever to a refinery, the energy and environmental burdens of running the refinery, and onward through the pump, through the car, and even when the car is decommissioned at the end of its life, we look at what kind of air pollution, particularly carbon dioxide, is evolved in that whole big sequence. And the reason that we have to do it that way is that the drive lines we're talking about are completely different, the fuels are different, and if we don't comprehend all those steps, then we can come up with the wrong answer. For example, you could say that an electric vehicle is completely clean because when you drive it, there's no exhaust pipe, there are no emissions, therefore it's clean. But you have to think about where did all those batteries come from, where did the electricity to charge those batteries come from, what do we do at the end of the life with those batteries that have special materials and so forth. So this is a big data-intensive exercise, but I'm just going to hit a few high spots, and then at the end there are three particular slides I want to focus on. Okay. So these are the kinds of fuels we've heard about this morning or you've read about on your own, and I'm just going to hit a page or two on each one of these. Natural gas can either be in compressed form or it can be at atmospheric pressure but absorbed in a special material in the tank. Biofuels, the most common of those that you've heard of is ethanol, corn ethanol. Coal to liquid, you've heard of probably tar sands, oil shale, a little bit more esoteric. Okay? So I'm not going to read all these slides to you, but you have your own copy or you can look at this on the screen. But this is our baseline, so gasoline and petrodiesel fuel are what we're going to measure everything else against. And coal to liquid, for example, sounds cool because you can clean up the coal, convert it to a liquid, and continue on as we are with a liquid fuel-based system. There's some significant emissions of carbon dioxide in the process, which we wouldn't catch if we just took that naive view of things. So there's something to be learned about that fuel, and it may be interesting down the road, okay? Oil shale you've heard of, it's out in my state of Colorado, Utah, Wyoming. And one of the problems you come up against that we catch in life cycle analysis is the so-called energy ratio. How much energy do you put in versus how much you get out? And we'd like that to be somewhat better than one, in other words, a number below one. But look at this. Here is oil shale down at the bottom. 2 lines above that are your Wheaties, your breakfast cereal. So that tells you right away that this oil shale is not a very energy intensive form of fuel. It's going to take a lot of material handling to get that stuff processed, and that means energy, okay? Tar sands are another energy-intensive fuel. They're becoming a big factor in Canada. The environmental burdens are significant. But basically what we do is strip mine certain parts of the surface of the earth, bake that product, and hope to extract some oil from it, okay? Those are the fossil fuels. Now, the biofuels that we want to talk about, you've heard of ethanol, of course. And the problem with ethanol is it takes a lot of water, it takes a lot of land, and it actually uses more petroleum in the big life cycle picture to make ethanol compared to just using the petroleum as gasoline directly. So when the decision in this country was made to look at corn ethanol, the picture that was, the snapshot that was taken was incomplete. In other words, you just looked at burning the stuff in the car. It seemed like a good idea. But this map here, for example, shows you where you would be growing corn to make ethanol. And if you put all of the agricultural land into growing corn for ethanol, you could only meet about half the energy requirements for light vehicles in the US. And the other thing that we just kind of tagged along here was water. You heard about that extensively this morning. But corn ethanol is a water-intensive fuel. And for example, to get that much, that 50% number I just mentioned, you'd need to have a few Mississippi rivers of water. And we don't have any spare water in this country, particularly in this part of the United States, for irrigation. It's basically for irrigation. And there's some water for the process itself. Okay? So let's forget corn ethanol. That didn't work out too well. We didn't look at it in the big picture. So next thing we look at is a cellulosic ethanol. And that is produced by plants that grow in land that isn't quite as valuable as corn. The downside of this next is that it takes some time to grow this, to process it, and so forth. And here are some other fuels you're going to hear about, sources of fuel. So we have the soybeans that are already being used to produce biofuels. You have corn, you have some of these oily plants here, and over in the right-hand column you see what the yield is. And it's not great, is it? It's in the 50s at the bottom end, up to the 80s toward the top end. It's another land-intensive aspect, but at least it's not the best farmland in the country that you need to do that. So we've looked at this from a life cycle analysis. Algae seems to be interesting. I don't know, how many of you have heard of algae fuels? Oh, this is great, because a couple years ago there would be nobody who even acknowledged it. But they're basically a broad spectrum of compounds or forms of algae that you can use to produce biofuels, namely ethanol and biodiesel. And the neat thing about these is that they're not land intensive, they're not water intensive, and they're very productive. Okay? This is what the so-called reactors look like, and in the lower left-hand corner you see one of the early ones is basically a bunch of plastic tubes with algae in there. And then on the lower right is a larger scale farm. But the neat thing about algae is that the water use is essentially zero because the water can be reused. And likewise, the land area is small. It's a very productive species. And then the really neat thing about this particular thing is that you can use the CO2 from power plants and other industries to make that algae reaction go even faster. So this is neat, isn't it? Because you can put it beside a power plant, you can remove all the CO2 from the exhaust of the plant and make a biodiesel out of it, or even ethanol. So this is a promising approach.